Lockheed Martin F-35 Lightning II is an American family of single-seat, single-engine, supersonic stealth strike fighters. A multi-role combat aircraft designed for both air superiority and strike missions. It also has electronic warfare and intelligence, surveillance, and reconnaissance capabilities. Lockheed Martin is the prime F-35 contractor with principal partners Northrop Grumman and BAE Systems. The aircraft has three main variants: the conventional takeoff and landing, CTOL, F-35A, the short takeoff and vertical landing, STOVL, F-35B, and the carrier-based, CATOBAR, F-35C. The aircraft descends from the Lockheed Martin X-35, which in 2001 beat the Boeing X-32 to win the Joint Strike Fighter, JSF, program intended to replace the F-16, FA-18, and the Harrier jump jet, among others. Its development is principally funded by the United States, with additional funding from program partner countries from the North Atlantic Treaty Organization, NATO, and close U.S. allies, including the United Kingdom, Australia, Canada, Italy, Norway, Denmark, the Netherlands, and formerly Turkey. Several other countries have also ordered, or are considering ordering, the aircraft. The program has drawn criticism for its unprecedented size, complexity, ballooning costs, and delayed deliveries. The acquisition strategy of concurrent production of the aircraft while it was still in development and testing led to expensive design changes and retrofits. The F-35 first flew in 2006 and entered service with the U.S. Marine Corps F-35B in July 2015, followed by the U.S. Air Force F-35A in August 2016 and the U.S. Navy F-35C in February 2019. The U.S. plans to buy 2,456 F-35s through 2044. Which will represent the bulk of the crewed tactical aviation of the U.S. Air Force, Navy, and Marine Corps for several decades. The aircraft is planned to be a cornerstone of NATO and U.S. allied air power and to operate to 2070. Program origins: the F-35 was the product of the Joint Strike Fighter, JSF, program, which was the merger of various combat aircraft programs from the 1980s and 1990s. One progenitor program was the Defense Advanced Research Projects Agency, DARPA, Advanced Short Takeoff, Vertical Landing, STOVL, which ran from 1983 to 1994. STOVL aimed to develop a Harrier jump jet replacement for the U.S. Marine Corps, USMC, and the UK Royal Navy, under one of STOVL's classified programs, the Supersonic STOVL Fighter, SSF. Lockheed Skunk Works conducted research for a stealthy supersonic STOVL fighter intended for both U.S. Air Force, USAF, and USMC. Among key STOVL technologies explored was the shaft-driven lift fan, SDLF, system. Lockheed's concept was a single-engine Canard Delta aircraft weighing about 24,000 pounds 11,000 kilograms, empty. A STOVL was rechristened as the Common Affordable Lightweight Fighter, CAF, in 1993 and involved Lockheed, McDonnell Douglas, and Boeing. The end of the Cold War and the collapse of the Soviet Union in 1991 caused considerable reductions in Department of Defense, DoD, spending and subsequent restructuring. In 1993, the Joint Advanced Strike Technology (JAST) program emerged following the cancellation of the USAF's multi-role fighter (MRF) and U.S. Navy's USN Advanced Attack Fighter (AFX) programs. MRF, a program for a relatively affordable F-16 replacement, was scaled back and delayed due to post-Cold War defense posture easing F-16 fleet usage and thus extending its service life, as well as increasing budget pressure from the F-22 Advanced Tactical Fighter (ATF) program. The AFX, initially known as the Advanced Attack AX, began in 1991 as the USN's follow-on to the Advanced Tactical Aircraft (ATA) program for an A6 replacement. The ATA's resulting A-12 Avenger II had been cancelled due to technical problems and cost overruns in 1991. In the same year, the termination of the Naval Advanced Tactical Fighter, NADF, a naval development of USAF's ATF program to replace the F-14, resulted in additional fighter capability being added to AX, which was then renamed AFX amid increased budget pressure. The DoD's Bottom-Up Review, BUR, in September 1993 announced MRF's and AFX's cancellations, with applicable experience brought to the emerging JAST program. JAST was not meant to develop a new aircraft, but rather to develop requirements, mature technologies, and demonstrate concepts for advanced strike warfare. As JAST progressed, the need for concept demonstrator aircraft by 1996 emerged, which would coincide with the full-scale flight demonstrator phase of STOVL, CAF, because the STOVL, CAF concept appeared to align with the JAST charter. The two programs were eventually merged in 1994 under the JAST name, with the program now serving the USAF, USMC, and USN. JAST was subsequently renamed to Joint Strike Fighter, JSF, in 1995, with STOVL submissions by McDonnell Douglas, Northrop Grumman, Lockheed Martin, and Boeing. The JSF was expected to eventually replace large numbers of multirole and strike fighters in the inventories of the U.S. and its allies, including the Harrier, F-16, FA-18, A-10, and F-117. International participation is a key aspect of the JSF program, starting with United Kingdom participation in the STOVL program. Many international partners requiring modernization of their air forces were interested in the JSF. The United Kingdom joined JSF as a founding member in 1995 and thus became the only Tier 1 partner of the JSF program. Italy, the Netherlands, Denmark, Norway, Canada, Australia, and Turkey joined the program during the concept demonstration phase, CDP, with Italy and the Netherlands being Tier 2 partners and the rest Tier 3. Consequently, the aircraft was developed in cooperation with international partners and available for export. JSF competition. Boeing and Lockheed Martin were selected in early 1997 for CDP, with their concept demonstrator aircraft designated X-32 and X-35 respectively. The McDonnell Douglas team was eliminated and Northrop Grumman and British Aerospace joined the Lockheed Martin team. Each firm would produce 2 prototype air vehicles to demonstrate conventional takeoff and landing, CTOL, carrier takeoff and landing, CV, and STOVL. Lockheed Martin's design would make use of the work on the STLF system conducted under the STOVL CAF program, the key aspect of the X-35 that enabled STOVL operation. The STLF system consists of the lift fan and the forward center fuselage that could be activated by engaging a clutch that connects the drive shaft to the turbines and thus augmenting the thrust from the engine's swivel nozzle. Research from prior aircraft incorporating similar systems, such as the Convair Model 200, Rockwell XFE-12, and Yakovlev Yak-141, were also taken into consideration. By contrast, Boeing's X-32 employed direct lift system that the augmented turbofan would be reconfigured to when engaging in STOVL operation. Lockheed Martin's commonality strategy was to replace the STOVL variant's STLF with a fuel tank and the aft swivel nozzle with a two-dimensional thrust vectoring nozzle for the CTOL variant. STOVL operation is made possible through a patented shaft-driven lift fan propulsion system. This would enable identical aerodynamic configuration for the STOVL and CTOL variants, while the CV variant would have an enlarged wing to reduce landing speed for carrier recovery. Due to aerodynamic characteristics and carrier recovery requirements from the JAST merger, the design configuration settled on a conventional tail compared to the canard delta design from the STOVL CAF. Notably, the conventional tail configuration offers much lower risk for carrier recovery compared to the STOVL CAF canard configuration, which was designed without carrier compatibility in mind. This enabled greater commonality between all 3 variants, as the commonality goal was important at this design stage. Lockheed Martin's prototypes would consist of the X-35A for demonstrating CTOL before converting it to the X-35B for STOVL demonstration and the larger winged X-35C for CV compatibility demonstration. The X-35A first flew on October 24, 2000 and conducted flight tests for subsonic and supersonic flying qualities, handling, range, and maneuver performance. After 28 flights, the aircraft was then converted into the X-35B for STOVL testing, with key changes including the addition of the SDLF, the 3-bearing swivel module, 3 BSM, and roll control ducts. The X-35B would successfully demonstrate the SDLF system by performing stable hover, vertical landing, and short takeoff in less than 500 feet, 150 m. The X-35C first flew on December 16, 2000 and conducted field landing carrier practice tests. On October 26, 2001, Lockheed Martin was declared the winner and was awarded the System Development and Demonstration (SDD) contract. Pratt & Whitney was separately awarded a development contract for the F-135 engine for the JSF. The F-35 designation, which was out of sequence with standard DoD numbering, was allegedly determined on the spot by Program Manager Major General Mike Hoff. This came as a surprise even to Lockheed Martin, which had expected the F-24 designation for the JSF. Design and production. Engineer handling a metallic scale model of jet fighter and wind tunnel. As the JSF program moved into the system development and demonstration phase, the X-35 demonstrator design was modified to create the F-35 combat aircraft. The forward fuselage was lengthened by 5 inches, 13 centimeters, to make room for mission avionics, while the horizontal stabilizers were moved 2 inches, 5.1 centimeters, aft to retain balance and control. The diverterless supersonic inlet changed from a 4-sided to a 3-sided cowl shape and was moved 30 inches, 76 centimeters, aft. The fuselage section was fuller, the top surface raised by 1 inch, 2.5 centimeters along the centerline and the lower surface bulged to accommodate weapons bays. Following the designation of the X-35 prototypes, the 3 variants were designated F-35A, CTOL, F-35B, STOVL, and F-35C, CV. All with a design service life of 8,000 hours. A prime contractor, Lockheed Martin performs overall systems integration and final assembly and checkout, FICO, at Air Force Plant 4 in Fort Worth, Texas, while Northrop Grumman and BAE Systems supply components for mission systems and airframe. Adding the systems of a fighter aircraft added weight. The F-35B gained the most, largely due to a 2003 decision to enlarge the weapons base for commonality between variants. The total weight growth was reportedly up to 2,200 pounds, 1,000 kilograms, over 8%, causing all STOVL key performance parameter, KPP, thresholds to be missed. In December 2003, the STOVL Weight Attack Team, SWAT, was formed to reduce the weight increase. Changes included thinned airframe members, smaller weapons bays and vertical stabilizers, less thrust fed to the rollpost outlets, and redesigning the wingmate joint, electrical elements, and the airframe immediately aft of the cockpit. The inlet was also revised to accommodate more powerful, greater mass flow engines. Many changes from the SWAT effort were applied to all three variants for commonality. By September 2004, these efforts had reduced the F-35B's weight by over 3,000 pounds, 1,400 kilograms, while the F-35A and F-35C were reduced in weight by 2,400 pounds, 1,100 kg, and 1,900 pounds, 860 kilograms, respectively. The weight reduction work cost $6.2 billion and caused an 18-month delay. The first F-35A, designated AA-1, was rolled out at Fort Worth on February 19, 2006 and first flew on December 15, 2006 with Chief Test Pilot John S. Beasley at the controls. In 2006, the F-35 was given the name Lightning II after the Lockheed P-38 Lightning of World War II. Some USAF pilots have nicknamed the aircraft Panther instead, and other nicknames include Fat Amy and Battle Penguin. The aircraft's software was developed as 6 releases, or blocks, for SDD. The first 2 blocks, 1A and 1B, readied the F-35 for initial pilot training and multi-level security. Block 2A improved the training capabilities, while 2B was the first combat-ready release plan for the USMC's initial operating capability. IOC. Block 3I retains the capabilities of 2B while having new technology refresh 2, TR2. Hardware and was planned for the USAF's IOC. The final release for SDD, Block 3F, would have full flight envelope and all baseline combat capabilities alongside software releases. Each block also incorporates avionics hardware updates and air vehicle improvements from flight and structural testing. In what is known as concurrency, some low-rate initial production, LRIP, aircraft lots would be delivered in early block configurations and eventually upgraded to Block 3F once development is complete. After 17,000 flight test hours, the final flight for the SDD phase was completed in April 2018. Like the F-22, the F-35 has been targeted by cyber attacks and technology theft efforts, as well as potential vulnerabilities in the integrity of the supply chain. Testing found several major problems. Early F-35B airframes were vulnerable to premature cracking. The F-35C arrestor hook design was unreliable, fuel tanks were too vulnerable to lightning strikes, the helmet display had problems, and more. Software was repeatedly delayed due to its unprecedented scope and complexity. In 2009, the DoD Joint Estimate Team, JET, estimated that the program was 30 months behind the public schedule. In 2011, the program was rebaselined, that is, its cost and schedule goals were changed, pushing the IOC from the plan 2010 to July 2015. The decision to simultaneously test, fix defects, and begin production was criticized as inefficient. In 2014, Under Secretary of Defense for Acquisition Frank Kendall called it acquisition malpractice. The 3 variants shared just 25% of their parts, far below the anticipated commonality of 70%. The program received considerable criticism for cost overruns and for the total projected lifetime cost, as well as quality management shortcomings by contractors. The JSF program was expected to cost about $200 billion for acquisition in base year 2002 when SDD was awarded in 2001. As early as 2005, the Government Accountability Office, GAO, had identified major program risks in cost and schedule. The costly delays strained the relationship between the Pentagon and contractors. By 2017, delays and cost overruns had pushed the F-35 program's expected acquisition costs to $406.5 billion, with total lifetime cost, i.e., to 2070, to $1.5 trillion in then-year dollars, which also includes operations and maintenance. The F-35A's unit cost, not including engine, for LRIP Lot 13 was $79.2 million in base year 2012. Delays in development and operational test and evaluation, including integration into the joint simulation environment, pushed full-rate production decision from the end of 2019 to March 2024. Although actual production rate had already approached the full rate by 2020, the combined full rate at the Fort Worth, Italy, and Japan FACO plants is 156 aircraft annually. Upgrades and further development. Sailors prepare to taxi an F-35C Lightning II on aircraft carrier USS Carl Vinson. The F-35 is expected to be continually upgraded over its lifetime. The first combat-capable Block 2B configuration, which had basic air-to-air and strike capabilities, was declared ready by the USMC in July 2015. The Block 3F configuration began operational test and evaluation (OTNE) in December 2018 and its completion in late 2023 concluded SDD in March 2024. The F-35 program is also conducting sustainment and upgrade development, with early aircraft from LRIP Lot 2 onwards gradually upgraded to the baseline Block 3F standard by 2021. With Block 3F as the final build for SDD, the first major upgrade program is Block 4, which began development in 2019 and was initially captured under the Continuous Capability Development and Delivery C2D2 program. Block 4 is expected to enter service in incremental steps from the late 2020s to early 2030s and integrates additional weapons, including those unique to international customers, improved sensor capabilities including the new and APG-85 AESA, radar and additional ESM bandwidth, and adds remotely operated video-enhanced receiver, rover, support. C2D2 also places greater emphasis on agile software development to enable quicker releases. The key enabler of Block 4 is Technology Refresh 3, TR3, avionics hardware, which consists of new display, core processor, and memory modules to support increased processing requirements, as well as engine upgrade that increases the amount of cooling available to support the additional mission systems. The engine upgrade effort explored both improvements to the F-135 as well as significantly more power and efficient adaptive cycle engines. In 2018, General Electric and Pratt & Whitney were awarded contracts to develop adaptive cycle engines for potential application in the F-35, and in 2022, the F-35 Adaptive Engine Replacement Program was launched to integrate them. However, in 2023 the USAF chose an improved F-135 under the Engine Core Upgrade (ECU) program over an adaptive cycle engine, due to cost as well as concerns over risk of integrating the new engine, initially designed for the F-35A, on the B and C. Difficulties with the new TR-3 hardware, including regression testing, have caused delays to Block 4 as well as a halt in aircraft deliveries from July 2023 to July 2024. Defense contractors have offered upgrades to the F-35 outside of official program contracts. In 2013, Northrop Grumman disclosed its development of a directional infrared countermeasure suite, named Threat Nullification Defensive Resource, THNDR. The countermeasure system would share the same space as the Distributed Aperture System, DAIS, sensors, and acts as a laser missile jammer to protect against infrared homing missiles. The United States is the primary customer and financial backer, with planned procurement of 1,763 F-35 as for the USAF, 353 F-35Bs and 67 F-35Cs for the USMC, and 273 F-35Cs for the USN. Additionally, the United Kingdom, Italy, the Netherlands, Turkey, Australia, Norway, Denmark, and Canada have agreed to contribute $4.375 billion towards development costs, with the United Kingdom contributing about 10% of the planned development costs as the sole Tier 1 partner. The initial plan was that the US and 8 major partner countries would acquire over 3,100 F-35s through 2035. The 3 tiers of international participation generally reflect financial stake in the program, the amount of technology transfer and subcontracts open for bid by national companies, and the order in which countries can obtain production aircraft, alongside program partner countries, and Singapore have joined as security cooperative participants, SCP, sales to SCP and non-partner states, including Belgium, Japan, and South Korea, are made through the Pentagon's foreign military sales program. Turkey was removed from the F-35 program in July 2019 over security concerns following its purchase of a Russian S-400 surface-to-air missile system. Design. The F-35 is a family of single-engine, supersonic, stealth multi-role strike fighters, the second fifth-generation fighter to enter U.S. service and the first operational supersonic STOVL stealth fighter. The F-35 emphasizes low observables, advanced avionics and sensor fusion that enable a high level of situational awareness and long-range lethality. Wink with around 91, 92, 93, the USAF considers the aircraft its primary strike fighter for conducting suppression of enemy air defense, SAD, and air interdiction missions. Owing to the advanced sensors and mission systems, the F-35 has a wingtail configuration with 2 vertical stabilizers canted for stealth. The flight control surfaces include leading-edge flaps, flaperons, rudders, and all-moving horizontal tails, stabilators, leading-edge root extensions or chins also run forwards to the inlets. The relatively short 35-foot wingspan of the F-35A and F-35B is set by the requirement to fit inside USN amphibious assault ship parking areas and elevators. The F-35C's larger wing is more fuel-efficient. The fixed diverterless supersonic inlets, DSI, use a bumped compression surface and forward-swept cowl to shed the boundary layer of the forebody away from the inlets, which form a viaduct for the engine. Structurally, the F-35 drew upon lessons from the F-22. Composites comprise 35% of airframe, with the majority being bismulimide and composite epoxy materials as well as some carbon nanotube reinforced epoxy in later production lots. The F-35 is considerably heavier than the lightweight fighters it replaces, with the lightest variant having an empty weight of 29,300 pounds, 13,300 kilograms. Much of the weight can be attributed to the internal weapons bays and the extensive avionics carried, while lacking the kinematic performance of the larger twin-engine F-22. The F-35 is competitive with fourth-generation fighters such as the F-16 and F-A-18, especially when they carry weapons because the F-35's internal weapons bay eliminates drag from external stores. All variants have a top speed of Mach 1.6, attainable with full internal payload. The Pratt & Whitney F-135 engine gives good subsonic acceleration and energy, with supersonic dash and afterburner. The F-35, while not a supercruising aircraft, can fly at Mach 1.2 for a dash of 150 miles, 240 kilometers, with afterburners. This ability can be useful in battlefield situations. The large stabilators, leading-edge extensions and flaps, and canted rudders provide excellent high alpha, angle of attack, characteristics, with a trimmed alpha of 50 degrees. Relaxed stability and triplex redundant fly-by-wire controls provide excellent handling qualities and departure resistance. Having over double the F-16's internal fuel, the F-35 has a considerably greater combat radius, while stealth also enables a more efficient mission flight profile. Sensors and avionics. The F-35's mission systems are among the most complex aspects of the aircraft. The avionics and sensor fusion are designed to improve the pilot's situational awareness and command and control capabilities and facilitate network-centric warfare. Key sensors include the Northrop Grumman and EPG-81 Active Electronically Scanned Array (ESA) radar, BAE systems, and ASQ-239 Barracuda Electronic Warfare System, Northrop Grumman Raytheon, and AAQ-37 Electro-Optical Distributed Aperture System, DIAS, Lockheed Martin, and AAQ-40 Electro-Optical Targeting System, EODIAS, and Northrop Grumman and ASQ-242 Communications, Navigation, and Identification (CNI) suite. The F-35 was designed for its sensors to work together to provide a cohesive image of the local battlespace. The APG-81 radar also acts as a part of the electronic warfare system. Much of the F-35 software was developed in C and C++ programming languages, while ATA-83 code from the F-22 was also used. The Block 3F software has 8.6 million lines of code. The Green Hills Software Integrity Do 178B Real-Time Operating System, RITOS, runs on integrated core processors, ICPs. Data networking includes the IEEE 1394B and fiber channel buses. The avionics use commercial off-the-shelf, COTS, components when practical to make upgrades cheaper and more flexible. For example, to enable fleet software upgrades for the software-defined radio, SDR, systems. The mission system software, particularly for sensor fusion, was one of the program's most difficult parts and responsible for substantial program delays. The APG-81 radar uses electronic scanning for rapid beam agility and incorporates passive and active air-to-air modes, strike modes, and synthetic aperture radar, SAR, capability, with multiple target track while scan at ranges in excess of 80 nmi, 150 kilometers. The antenna is tilted backwards for stealth. Complementing the radar is the AAQ-37 DAS, which consists of 6 infrared sensors that provide all-aspect missile launch warning and target tracking. The DAS acts as a situational awareness infrared, search and track, SARST, and gives the pilot spherical infrared and night vision imagery on the helmet visor. The ASQ-239 Barracuda Electronic Warfare System has 10 radio frequency antennas embedded into the edges of the wing and tail for all-aspect radar warning receiver, RWR. It also provides sensor fusion of radio frequency and infrared tracking functions, geolocation threat targeting, and multispectral image countermeasures for self-defense against missiles. The electronic warfare system can detect and jam hostile radars. The AAQ-40 EODIAS is mounted behind a faceted low observable window under the nose and performs laser targeting, forward-looking infrared, FLIR, and long-range IRST functions. The ASQ-242 CNI suite uses a half-dozen physical links, including the Directional Multifunction Advanced Data Link (MADL) for covert CNI functions. Through sensor fusion, information from radio frequency receivers and infrared sensors are combined to form a single tactical picture for the pilot. The all-aspect target direction and identification can be shared via MADL to other platforms without compromising low observability. While Link 16 enables communication with older systems, the F-35 was designed to accept upgrades to its processors, sensors, and software over its lifespan. Technology Refresh 3, which includes a new core processor and a new cockpit display, is planned for Lot 15 aircraft. Lockheed Martin has offered the advanced EOTS for the Block 4 configuration. The improved sensor fits into the same area as the baseline EOTS with minimal changes. In June 2018, Lockheed Martin picked Raytheon for improved DAS. The USAF has studied the potential for the F-35 to orchestrate attacks by unmanned combat aerial vehicles, UCAVs, via its sensors and communications equipment. A new radar called the APG-85 is planned for Block 4 F-35s. According to the JPO, the new radar will be compatible with all three major F-35 variants. However, it is unclear if older aircraft will be retrofitted with the new radar.